Ever look at a massive structure and wonder what keeps it standing? What's the difference between a building that survives a disaster and one that just doesn't? Well, it's not magic, and it's not just about being strong. It's actually a fascinating dance between three invisible rules of engineering. Let's get into it.
Okay, take a look at these two buildings. On the left, you got the Murrah Federal Building, after the 1995 bombing, a total catastrophic collapse. But on the right, that's 130 Liberty Street. It was absolutely slammed by debris from the World Trade Center, yet it stayed standing. Both were hit with incredible force, but the outcomes couldn't be more different.
So, what gives? What is that invisible secret that decides if a building crumbles like a house of cards or just stubbornly refuses to fall? Well, that's the big question we're going to answer right now.
We're going to break this all down into three key ideas that engineers live and die by: stiffness, flexibility, and something called redundancy. Trust me, by the end of this, you're going to see the world around you a whole lot differently.
All right, first up, stiffness. This is the one we all kind of get, right? It's a structure's ability to resist being bent out of shape. But, and this is a big but, stiffness has a hidden and sometimes really dangerous dark side.
Now, before we go any further, let's clear something up real quick. Stiffness is not the same thing as hardness. Hardness is about resisting a scratch or a dent on the surface. But stiffness, that's all about a material's guts, its ability to take a load, not bend, and then spring right back to its original shape.
The fancy engineering term for this is tensile modulus. So if something has a high modulus, it can take a ton of stress without even budging. Think about something like cast iron or a big slab of concrete.
But here's the catch. This is the critical trade-off. As our source material points out, things that are incredibly stiff, that have that high tensile modulus, they also tend to be brittle. They resist and resist and resist, and then they just snap. No warning.
Here's the perfect way to picture it. A concrete cinder block, right? It can hold up a ton of weight without being crushed. Super stiff. But what happens if you drop it? It doesn't bend, it doesn't dent, it explodes into a million pieces. That sudden catastrophic failure, that's brittleness.
And this right here, this is what that cinder block looks like on the scale of an entire building. It's not a slow, graceful bend, it is a sudden, explosive crack. When a material is all stiffness and no give, this is what happens. And that is exactly why stiffness alone is not enough.
So if stiffness has this dangerous side, it needs a partner, right? Something to create balance. And that brings us to our second concept, flexibility. This is the superpower of being able to bend and deform and give a little bit under pressure without actually breaking.
You actually see this principle every single day. Just think about the plastic clip on a battery cover. It has to bend to snap into place. If that little piece of plastic was as stiff as our cinder block, it would just break the first time you tried to use it. It needs that flexibility to do its job.
The engineering word for this is ductility, and it's basically a measure of how much something can stretch or bend before it finally fails. See, a ductile material gives you a warning. It bends, it groans, it absorbs energy, it tells you something is wrong before a total collapse. It's the opposite of that sudden, brittle failure we saw earlier.
Okay, let's go back to that first image. The investigation into the Murrah building found that the structure basically behaved like a giant cinder block. It was a standard concrete frame that just didn't have the ductile design needed to absorb the energy from the blast. When a few key supports were gone, there was zero flexibility in the system to cope with that loss.
And get this. The official investigation concluded that if the building had included design features that are common in earthquake zones, features specifically designed to add ductility, over half of the area that collapsed could have been saved. That's the life-or-death difference flexibility makes.
Okay, so we have stiffness to resist force and flexibility to absorb it. But what happens if a piece of the structure fails anyway? Well, that's where our third and final principle comes in, redundancy. You can just think of it as the ultimate plan B.
So, how does redundancy work? It creates what engineers call alternate load paths. Imagine you're driving, and the main bridge is out. A good road system has other routes, right? Detours to get you around the problem. It's the same idea in a building. If a column gets knocked out, the weight it was carrying can find a new way to the ground through the beams and columns around it.
And there is no more powerful, more dramatic example of this than the Pentagon on September 11th. Look at this damage. It's just terrifying. Dozens of columns on the first floor were just gone, completely destroyed or damaged. Logically, everything above that should have pancaked instantly.
But it didn't. So why not? Because the Pentagon was, without a doubt, a masterclass in redundancy. It had those alternate load paths. It had continuous steel reinforcement tying everything together. It had ductile columns. It basically had a plan B, C, and D engineered right into its DNA from day one.
The result was, honestly, nothing short of a miracle. That heavily damaged section of the Pentagon stayed standing for almost 20 minutes after impact. That delay, bought and paid for by redundancy, gave people upstairs a window to escape before a much smaller, localized collapse finally happened. Redundancy flat out saved lives.
So, how do we put this all together? Well, stiffness, flexibility, and redundancy aren't rivals. They're actually partners, and together they create what we call resilience. See, the real secret to a tough design isn't to max out any one of these things. It's all about creating a balanced system. The key, as engineers say, is to make sure all the parts are effectively tied together, so the whole structure acts like one big, interconnected team, not just a bunch of separate pieces. So what does tying a building together actually look like? Well, check this out. This is a detail from the Khobar Towers in Saudi Arabia. See those overlapping steel loops? They would thread a steel cable right through them, literally locking all the concrete floor panels together into one continuous system. And here's the payoff. In 1996, a massive truck bomb went off right next to the building and blew the entire face of it clean off. But because everything was tied together so well, the collapse didn't spread. The building took the hit, but it refused to fall like a house of cards. That is a testament to resilient design.
You know, these principles are everywhere, not just in giant buildings. They're in technology, they're in nature, they're even in how successful teams work. So the next time you look at a bridge or a tree bending in the wind, ask yourself, okay, where's the stiffness? Where's the flexibility? And what's the plan B? You might be surprised at what you start to see.